there was a lot of variables, right? There was pressure, temperature, volume, and number of moles. And today we're going to focus on that number of moles because that allows us to do stoichiometry. So if you go back to your first semester talking about mole ratios in a balanced chemical reaction and so on, we're going to do some problems related to that today. And then we'll go back on Monday. I've changed the title of Monday's lecture a little bit. It's going to be talking about gas density and about effusion, like how we can tell the difference between gases and how fast they go. So we'll learn about gas velocities and stuff on Monday. But I wanted to just take a little side trip today and refresh your memory on some of the stoichiometry calculations that you used to do, and we'll add in the gas part. So that makes it a little more complicated. But it's also I want to introduce this term that I use. So this is a particular situation where your professor is giving you something unique, a new term that's not in any of the books, and it's called lab units. And I contrast that with chemistry units. So the chemistry units are moles, of course, but the lab units are all the things that you can measure with your hands. Okay, so that's the distinction that I want to talk about. But before we get there, let's think about Avogadro's law. He said that, you know, at the same temperature and pressure, if you have the same volume of a different gas, you have the same number of particles. So this is what allows us to do stoichiometry. So if we measure the volume of a gas or the pressure at a gas at a particular temperature, then we can know the number of particles or the number of moles that are in that. And so this is what we see in terms of our volumes. If all of our balloons are 1 liter balloons, say, and you have a 1 liter of nitrogen, you can mix it with 3 liters of hydrogen and make 2 liters of ammonia. Okay. And so we could do stoichiometry with volumes. We could do stoichiometry with pressures, and we'll do partial pressures next. But Avogadro's law lets us tie that down to particular molecules and particular moles of molecules. You know, a molecule is way too small to measure the mass, obviously. Like if you go to a hardware store and you want to buy nails or something, they're not going to count out a dozen nails. They're going to weigh them, okay? And so they have some conversion inside their computer that converts that to mass, converts that mass into a number of nails and so on. Likewise with molecules, we don't count individual molecules. We have to have some number that corresponds a measurable amount of molecules, and that number is Avogadro's number. So instead of 12 being a dozen, we have 6 times 10 to the 23rd being a mole. So it's 6 times 23rd particles is a mole of that substance. Now that's a number, and that number of carbon atoms weighs different than that number of hydrogen atoms. And that's where we have the masses on the periodic table. Those tell you the masses of a mole of each of those substances. Now, in terms of counting volumes, we need to have a standard temperature and pressure. And so since that number of moles in a given volume varies with those two things, the pressure and temperature, we come up with standard temperature and pressure. Now, you know, we deal in atmospheric pressure, so that's pretty easy to remember. But how can you remember the temperature for standard temperature and pressure? It's not room temperature. You know, last time we talked about room temperature being 25 degrees C. Okay. How do we know that standard temperature, though, is 0 degrees C? And just think about it. If in the old days, if they were going to measure a standard volume, they had access to ice water. And so just think about how you would make that measurement. You put ice in water, let it come to thermal equilibrium at 0 C. You could submerge a container of gas that's flexible like a balloon into that water. It would come to 0 degrees C, and then you could measure the volume at standard temperature and 1 atmosphere pressure. So that's how you can remember what STP is. It's ice water at 1 atmosphere. Now, how do we deal with mixtures of gases? Well, this is Dalton's law of partial pressures. And it's pretty simple. It's just saying that all the different molecules in a container are hitting the walls, and they're all exerting pressure. And the total pressure is the sum of the partial pressures. Each gas hits that wall in proportion to the number of particles of that gas. And so if it's a 50-50 mixture, then half the gas 1 is going to be giving you half that total pressure, and the other half is gas number 2 giving you the rest of that total pressure. So the pressures just add up because it's molecules hitting the walls of the container. And this works just fine. So you can take the 300 kilopascals, add 600, add 450, and you get the 1350. That's the partial pressure, adding up to the total pressure. So just a very logical concept to think about. But that's the law, Dalton's law of partial pressures. Let's do some math with this, and let's think about how we can understand the number of moles in this container. And so let's just focus on this first gas, the one that has 300 kilopascals. If we look to see what pressure is, that's the number of moles of that substance times the RT divided by the total volume. And the P total is the total number of moles in the whole container times RT over the total volume. And look at all the things that cancel. The R cancels, T cancels because they're at the same temperature. They're both in the same container. And so this is just the number of moles of substance 1 divided by the total number of moles. And so what we're getting is a mole fraction. You could take the partial pressures and you could determine the concentration of that gas in this container. And that concentration in this case is called mole fraction or mole percent. And we give that the symbol X. So if we have 300 kilopascals for the partial pressure of gas 1 and the total is 1350, then that's going to be 300 divided by 1350 or 0.22. So all of the mole fractions are going to be less than 1. And so they'll be from 0 to 1. You multiply them by 100%, you get the percent concentration. And that's, in terms of moles or particles, that's the concentration of this substance 1. Very important concept. So I'm going to pause here to see if there's anything that you need clarified. Okay, don't be bashful. So it's real easy to calculate mole fractions if you have the partial pressure and the total pressure. A lot of times we're given these mole fractions. Like we might say that oxygen is 21% of the atmospheric concentration. And so that's telling you there's 21 moles of oxygen for every 100 moles of gas particles in the atmosphere. And so this is a mole percent that we're talking about. How do we do this in lab? How do we collect volumes of something? Well, one of the ways to do that is by water displacement. So I think this is a great illustration of a cool reaction. You can fill that Erlenmeyer flask up with water and put it upside down inside a tank of water, and you can have a little tube go under it. In reality, a lot of these tanks have a little valve down here at the bottom where the tube comes to the middle and comes in through the bottom of the tank. Because if you're looking at that apparatus, you're like, how can that work? You know, what's holding the flask and so on. So this little hole in the bottom of the tank is hooked up to the reaction flask, like this. Okay. And it bubbles. And what you do is you trap that gas, and you can easily measure the volume that this reaction produces over time and so on. You can make this temperature of this liquid. You could put ice in there so you can make it standard temperature and pressure. So that would be our standard temperature, 1 atmosphere pressure. You could correct this for atmosphere if you measured the barometric pressure, but you could assume we're at 1 atmosphere. We have 273 Kelvin for the ice water temperature, and then you would have a standard amount of gas that you're collecting, and you could keep track of reactions. And you could say, well, does this, we put so many moles of this substance into the reaction and so many moles of that, and it produced a certain amount of gas. Well, you could measure how many moles of gas it produced by trapping it this way. The only one issue we have here is we have the vapor pressure of water. So this isn't pure gas. It has the vapor pressure of water. So you would need to subtract the partial pressure of water so that you get the number of moles of the gas that you're collecting. So that would be the only trick that you would have to do with that. So let's talk about this idea of lab units and chemistry units. So in this balanced chemical reaction, this is the combustion of methane, or natural gas. We have one molecule of methane reacting with 2 molecules of oxygen to produce a molecule of CO2 and 2 molecules of water. Notice we haven't lost any types of elements and so on, so mass is conserved. And so it's a balanced reaction. This could also mean moles. So a mole of methane reacts with 2 moles of oxygen to produce 1 mole of CO2 and 2 moles of water. So these coefficients in front of all the substances are telling you how many moles of each substance are traded around or consumed or produced. You could even put plus and minus signs on here. You could say, we take away 1 mole of methane and we take away 2 moles of oxygen and we produce 1 mole of CO2 and produce 2 moles of water. So the reactants are subtracted and the products are added, like they show up. Well, that's what I'm calling chemical units, because that's how chemistry happens. It happens between particles, but we can't really see individual particles or measure them, so we measure moles of particles, but it's the same thing. Okay. And then when we go into the lab, how do we know this is happening? Well, we measure volumes, or we measure masses, or we measure pressures. Okay, so we could, this same reaction, the same actually 1 mole of methane would be 22.4 liters of methane at STP. So we would go down 22.4 liters of methane, we would go down 44.8 liters of oxygen, and we would produce 22.4 liters of CO2 and produce 44.8 liters of water at STP. So if we were collecting this reaction, actually, if this were taking place in that flask and we had it hooked up to the bubbler, notice the number of liters on the left is equal to the number of liters on the right. So we wouldn't get any excess bubbles over here. It would just all take place in that container, and we would go from 3 total liters to 3 total liters, but it would be from oxygen and methane would turn into CO2 and water. Now we would know something happened because that would generate a lot of heat. So it wouldn't create any more gas, but it would heat up the gas, and then that gas would expand. So that would be something that it wouldn't be at STP though. Same thing with mass. So we would lose 16 grams of methane. We would lose 32 grams of oxygen. We would gain 44 grams of CO2 and gain 36 grams of water. Okay. Something. I think this isn't right. This actually should be 64, I think. Right, it's 2 moles of oxygen. Yeah, 64. I was going to say, it adds up, right? We have 64 and one is 70, 80. And then over here we have 44, 7, 6, it's 80. So 80 grams and 80 grams. So mass is conserved. I saw that and I was like, wait, that mass isn't conserved, but it is. It should be 64. And then if we have it in a container, 1 liter container, and so we have a rigid container and it's at 273, then we would have a partial pressure of methane reacting with the 2 atmospheres of oxygen. So it's sort of a 33 partial pressure, 0.33 here, and 0.67 for oxygen. Those would react and produce the CO2 and water. Okay. So these are what I'm calling lab units. Because in the lab we have things that measure pressure, and we have things that measure mass, and we have things that measure liters. Okay. And so those are the units that you're going to start with in problems. They're going to say things like 4 liters of this or 16 grams of that. And that's not chemistry units. You have to convert over to chemistry units, get it into moles, and then do the math. So let's do a problem.
Real quick.
Yeah.
So do you subtract track the atmospheric pressures too? So would that be negative and negative?
Yeah. So if these two things produced solids, then you would see a decrease in pressure. You could create a vacuum that way. Yeah. So if you had something that reacted to create a solid and all the gas went away, you'd have a vacuum.
So it's not always going to be negative, negative, positive, positive. It can be like positive, negative.
Well, in this particular case, this arrow is what makes the difference. And so all your reactants are negative, and all your and all your products are positive. And I'll show you where that comes in. Yeah. I'm just trying to get your mind to think, okay, reactants are going away and products are appearing. That's the whole purpose of the pluses and minuses. So how many grams of water will be produced from the combustion of 16 grams of methane and excess oxygen? We actually saw the numbers before, but let's do this problem 3 different ways. Okay. So for step 1, balance the chemical equation. It's always step 1. You got to know what's going on with the molecules. Step 2, convert from grams to moles. And so we've got 16 grams of methane. We're going to convert that to moles by dividing by the molar mass. So this one, where'd that 16 come from? This is 12 plus 4. So 12 is the carbon and 4 is the 4 hydrogens. Okay. So I'll do this. So 12 times 1, because we have 1 carbon, and 4 times 1. Well, that's confusing. Anyways, 12 plus 4, that's the mass of methane. And then this 16 comes from the problem. So I try to make things easy, but I'm afraid sometimes it confuses people when there's too many numbers that are the same. Okay, so 16 divided by 16 is 1. So we have 1 mole of methane. So we convert it to moles. Now we're in chemistry units. Then we multiply by the mole ratio from the balanced chemical equation. So we're going to water, right? This is asking how many grams of water. All right, so that's water. So this is where we want to go. So it's on top. And methane is where we are, so it's on bottom. Okay. And so it's a 2-to-1 ratio. So we'll produce 2 moles of water from 1 mole of methane. We get that from the balanced chemical equation. Hopefully this is review. This is Chem 1 stuff that we're talking about. And then we convert those units to the units required by the problem. So we look back at the problem and we say, okay, it's asking for grams of water. Okay, so that's pretty straightforward. We have 2 moles of water times its molar mass. So that 18 is 2 times 1 plus 1 times 16 equals 18. Okay. And we end up with 36 grams of water. So that's the stoichiometry problem done in 3 parts. Now, in your practice, how many people condense this into one long train of things? So let me see a show of hands. Raise them high so I can kind of see. Okay, so it looks like a lot of people are comfortable with the next way. So this is the first way to do it. This is the next way.
Can you go back for like 2 seconds?
Yeah, sure.
I'm sorry.
No, that's not a problem.
So are we doing, all we're doing right now is just a long train of dimensional analysis?
Yeah, that's right. That's all we're doing right now. Yes. It's just a bit of review, get kind of a warm up, okay, for the semester. Okay, so then in one long train, again, the same steps, but I've color coded them because they're all in one long train. Okay, so the first step, balance the reaction. Second step, convert grams to moles. That's the black step there. The blue step is mole ratio. The green step is convert back to whatever mass or thing the problem is asking for. So I just wanted to reestablish stoichiometry that you learned in the first semester. Now we're going to add in the gas laws, okay, and see how those figure in, okay? Because they're not as convenient as this, because you have so many variables. And so how do you put PV equals nRT into this problem, right? It's in the first and last step. And so let's talk about a different way to do this problem, okay? So this is the third way to do this problem. And I know that a lot of you raised your hands. You're comfortable with this way of doing it. That's great. I'm not trying to knock you off that, okay? but I am trying to give you a tool for how you think through these problems. And so I'm going to introduce something next. It's called the mass action table. Because see, when we're in the lab, we see masses changing. We're seeing 16 grams of methane turn into 36 grams of water. And so this is a mass action. That's one of the things that they called it in the past. Stoichiometry is another name for that. Okay. And so here we could do this whole problem in table form. And this is important because this sets up a way to do the problem that will work with kinetics, and it sets up a way to do the problem that will work with equilibrium. And since that's where we're going, I want to introduce this now, where we can do the same stoichiometry problem with a table that we'll later be doing with equilibrium and with kinetics. Okay? So there's nothing magical about this table, but this table captures every possible question that I could ask you. So it's kind of like Sudoku, right? If you fill in all the squares, you know exactly what goes in every square. This is way more fun than Sudoku. Okay, that is 81 if-then statements. Totally boring, right? If there's a 9 in the column, this isn't a 9. If there's a 9 in the row, it's not 9. If there's a 9 in the square, it's not. In fact, I wrote an Excel spreadsheet to solve those things because it's only 81 if-then statements. It's pretty straightforward, okay? So this only has so many squares. It's much less than Sudoku. And going from row to row, you have unit conversions and so on. The chemistry happens in the middle. You see that chemical reaction. So let's just, in any reaction, we can start out with the balanced chemical equation at the top. We can set up the table. In our problem, we had 16 grams initially of methane, and I call it this initial lab units, right? So this is where we are. We're in the lab units part. We have excess oxygen. We haven't been told that there's no CO2 or water, so that's an assumption, but let's just assume there's none. Yes?
How did you determine that the oxygen was the excess? Is it just because it weighs more and it has more moles?
No, let's go back to the problem. It says, excess oxygen. So it says, okay, that's fine. Yeah, that was a good question. No, if it wasn't given, if you have no amount of oxygen, then, the only way that the 16 grams could completely go away is if you had excess. So that might even be an assumption, okay? So even, like if this was a written out problem, that's where you put your assumptions. I'm assuming there's no water yet. I'm assuming there's no CO2, and I'm assuming I have plenty of oxygen to take care of the combustion. Sounds good. Okay, so these, I'll go ahead and write these up here as assumptions. Now here's where the minus and pluses come into play. When I was introducing that earlier, is how this chemical reaction proceeds. These X's are moles. This little x is a mole. Okay. We don't know what the value is yet. It's not. Now in this particular set of notes, we have earlier we talked about X being mole fraction. We're in a different section of notes now, okay? This X is just a placeholder. It's a variable. And we're figuring out in this transition how many moles are changing places. And so we have up here a 1 in front of that methane, so we have minus X. We have a 2 up here, so we have minus 2X. So that 2 came from this 2. There was a 1 here from the CO2, so that's a 1 there, and we had a plus 2 for this. That came from that water right there, okay? And so you can always write out the chemical change row easily, just using X's and saying the coefficients in front of each species. The beautiful thing about this table method is once you discover what X is, it's the same for the whole table. Yeah, that's the key right there. And that will then allow you to answer all of the other squares. Once you find X, you have it for the whole table. You can find every square in the whole problem, okay? So what we have is this 16 grams. We need to get that into the initial chemical units, okay? So that's the mole fraction. Mole, that's the molar conversion, converting from grams to moles. And then we go across to the water column, and then we calculate how many grams of water we have. So it's still the 3 steps. This middle piece is that mole ratio. So let's go ahead and do that. 16 grams is 1 mole of methane. Okay. We have the calculation on an earlier page. Okay. Now, how do we figure out what X is? We're completely combusting the methane, so we end up down here at 0 grams. We're using it all up, so we have 0 moles here. And this is a simple math problem. 1 minus X equals 0. It doesn't get any easier. X is equal to 1, and so X is equal to 1 mole. And once we have X, we have it for the whole table. So X is 1 mole. So over here I have whatever water I have plus 2 more moles of water. So it doesn't mean that I have to start with 0, but I'm assuming I started with 0. But let's say I had 5. Well, now I got 2 more, and I would end up with 7. So anyway, we start out with 0 moles of water plus 2 moles gives 2 moles of water. And then we multiply that by 18 grams per mole, and we end up with the 36 grams. Okay, so that's using the mass action table to do the same problem. You know, this piece right here, this 1 right there and the 2 here, that's what took care of that mole ratio step. The nice thing about this is I could figure out how much oxygen I used up, right? And so how much oxygen did I use up? I used up 2 moles, right? If I started out with excess, I have now excess, CESS, minus 2 moles.
These completed tables, I guess, on Blackboard as well?
No, you just go to the video.
Oh, okay.
Yeah, and so you just scroll through until you find it. Yeah.
Thank you.
Yeah, excellent. Okay. And so this is, now let's add in the gases. So this is the new part. We've done stoichiometry first semester. It's a quick review. And now we'll add in the gases. So what volume of water will be produced from the combustion of 22.4 liters of methane and excess oxygen at STP? Notice I have to have some temperature and pressure if I'm going to be doing volumes. And so it's real simple to say at STP, then you know what the temperature and pressure are. So first we balance the chemical equation, then we convert lab units to chemical units, unites, little typo there. Okay. And so we use the ideal gas law. Solve it for N. 1 atmosphere pressure is the standard. 273 is the temperature standard. And then we have the gas constant. 22.4 liters of methane, that ends up to be 1 mole of methane. Then multiply by the mole ratio, that 2-to-1 ratio, 2 moles of water. And then this is asking what volume of water. So our lab units that we want in the end is volume at STP. And so we can convert that 2 moles of water into volume at STP. So temperature's on top now, pressure's on bottom. We end up with 44.8 liters of water. So this is the stoichiometry done with gases, but just notice the second and fourth step are using the gas law instead of using the straight unit conversions.
Do you care if we use 273 Kelvin or 273.15?
It's just kind of gauge it by how many sig figs you have in the problem. Like I'm only giving you 3, so you really don't have to have 5 in your temperature. Yeah, yeah. And so we could do the same thing with our mass action table, but this first step is the initial chemical units. And so we would use the ideal gas law to do that one. We still have the same 0 moles of methane, and so down here instead of the 0 grams, we would have 0 liters. Okay. But we would solve for that X and see that it's 1 mole again. We have 0 moles of water. We'd end up with 2 moles of water. So this middle part, notice the chemistry part of it didn't change at all. What changed is what we're measuring in the lab units. We're measuring volumes, and so that's what our apparatus is. We're going to want volumes of water, and so then this last thing is convert from moles to volume, 44.8 liters. I know that you're comfortable. Many of you, I saw you raise your hands. You're comfortable with the other sort of unit conversions, and it's easy to just start doing that with the PV equals nRT. And if you want to do the problems that way, that's fine. If you show your work and you do it right, you get full credit. I'm not going to make you do this table for stoichiometry problems. I will want to see this table for equilibrium problems. And so that's why I'm introducing it now, so you can kind of get ahead of the equilibrium pieces, especially since you're probably going to see it in the lab before we lecture on it in class. Okay, so this will get you ready for those lab problems. You'll see ICE tables is what they call them, initial change equilibrium, ICE. And so you'll see those in the lab, and this is setting you up for success by saying you've got lab units, get those into moles, then do the ICE table, and then go back to lab units, whether you need grams or pressure or volume. Then you're set. Okay, so that's the end of the prepared notes. Let's do some of the other squares that we have in here. Okay. So let me bail out of this real quick. Let's see. Okay. So I'm going to take this last problem, copy, paste, and get rid of the arrows. Okay, so there's the problem we have left off. Now let's say excess, let's say we actually knew what this was. What happened? Oh, that's crazy. What happened to that? Okay, let me try this.
Cool design.
Yeah, okay, duplicate. Is it working now? Okay, that's good. Okay, how about that? Okay, good. Let me make sure we're still recording. Yeah, we're good. Okay. Okay, so here we go. Let's put some numbers on here. Let's say we already had, I don't know, you want to say 20 liters of CO2? So 20 liters at STP. How much CO2 do we have at the end? Okay, so that's a complicated problem. I give you 22.4 liters of methane and 20 liters of CO2 and excess oxygen, and I ask you how much CO2 do you have in the end? So you got to do the methane stoichiometry, and then you got to add in the CO2 to get to the total amount. But it's easy on this table. If you were trying to do this with just your 3 steps, it would not be easy with the 3 steps, okay? But with the table, you have a very organized way to think about the problem, and that's what the table is. It's a way to think through the problem. Okay, so let's figure out how many moles 20 liters of CO2 is. It's not 22.4, so it'll be slightly less than a mole, okay? But let's go ahead and do the ideal gas law on that one. So N is equal to 1 atmosphere times 20 liters.
Where did you get the 20 from?
I just made it up.
Oh.
Yeah. All right. So instead of none, I just said, let's start with 20, and we'll see what we end up with the end. Okay. And so someone do that for me. Let's see. It's probably 0.9. What would you guess? Or what do you have on the calculator? Because if 1 mole is 22 and this is 20, it's about 10% low, so that would be 0.9. .09. 0.89. Okay, no, that's cool. Yeah, so we'll say 0.89. How about that? So I have 0.89 moles. And when I went from 1 minus x equals 0, x here is equal to 1 mole. Okay? And since x is equal to 1 mole, it's equal to 1 mole over here. So I have 0.89 plus 1 is equal to 1.89 moles CO2.
You're getting the 1 because of the balance equation. It's a 1-to-1 ratio on them.
Yes. Mm-hmm. And notice I'm not using this 0.89 in any kind of multiplication thing. I'm saying I get 1 more mole of CO2 from the reaction, and I add that to the 0.89. So that's where this table is really essential, is if you have initial conditions or limiting reactants, then this table will help you figure that out. And we'll do more practice on this next Wednesday. Okay? We'll do the limiting reactant problem. I'll have some over here, and we won't have excess oxygen. We'll run out of either oxygen or methane. Okay? But we'll use the table. But now we take 1.89. Okay. If you want to see a trick on this, at STP, remember we're at STP, right? So So if you're at STP, 1 mole is 22.4 liters. We verified that over here, right? We had 22.4 liters is 1 mole. And so I could say 1.9 moles of CO2, 1.89 moles CO2 times 22.4 liters per mole. Totally legit. Because that already contains the 0.0821 and the 273 and the 1 atmosphere. And so someone do that for me if you would. Okay, 42 point. That's good.
Yeah.
Liters CO2. All right, 40. I'll say 42. Isn't that cool? That's a complicated problem if you got that in the text. Now, the real trick is then to take the text. We've got time. I'll go ahead and create a new blank sheet, and I'll write out the text of the problem we just did. So we're kind of doing it backwards. We did the math first, and now we'll write out the text. But I want you to be able to read the text and say, okay, that table contains what this text is telling me. Make sense? So let's convert this math into a word problem. All right, so let me escape, keep, okay. All right, here we go. It bailed out again, didn't it? That's crazy. I don't know why it does that. Okay. There we go. That's what I wanted right there. Yep. Okay, so And I just put this little note, all volumes at STP, okay? So I'm saying, how many liters of CO2 do you have if you started with 20 liters of CO2 and burned 22.4 liters of methane in the container? So I don't put in oxygen. I'm making you assume that you have excess oxygen, okay? You can't assume that you started with 0 liters of CO2 because this is telling you had 20 liters of CO2. And so if you're trying to figure out what to start with, what to end with, and which little factors to include, like you can't do this kind of problem where you end up with liters of CO2 on the right and you have liters of methane. And that's the other thing, I wrote out methane. You should know that methane is CH4. Okay, so there's a vocabulary word there. We can you can talk about that later. But yeah, I could have written carbon dioxide too and make you remember the naming of carbon dioxide. So yes, you could convert this to moles. And you could convert this to moles of CO2. But if you just go straight over to liters of CO2, you end up with 1 liter of CO2, not 1.89. Okay. And so you could probably go all the way to this, to liters of CO2 and equals 1 liter of CO2. And then you'd have to add in the, let's see, is that right? No, we end up with 22. Yeah, it was 22.4 liters of CO2. And then we have to add in the 20. So some of you will like this way of doing it. That's fine. I like the table. I like to be able to find my way around the table and use my little X mole fraction helper, and then I can fill it out. And I think this is a much more organized way to approach the problems. And I'm just trying to set you up for success with equilibrium, because with equilibrium you have to use the table. Okay, and that's enough for today. Unless you have questions, well, we've got enough time, but you can come up and ask your questions individually. Y'all have a great weekend.
You as well. Have a blessed one.
Yeah, very good. And come sign the roster. It's right here.